How much weight can a boat hold? I wanted to do this problem in my calculus class that I teach the other day, but I didn't have time, so I want to go through it right now. The design of boats is based on Archimedes' principle, which states that the buoyant force of an object in water is equal to the weight of the water displaced. Suppose you want to build a sailboat whose hull is parabolic, shaped like this, which is not realistic, but it's simple, with cross-section y equals ax squared, where a is a constant. The graph that you see right there has that equation. It's assumed you put the x-axis going to the right this way and the y-axis going up like that. Your boat is going to have length L that you see right there and maximum draft, capital H, that you see right there. That's the maximum vertical depth of any point in the boat beneath the waterline. Every cubic meter of water weighs 10,000 newtons. In other words, the weight density of water is 10,000 newtons per cubic meter. The question is, what is the maximum possible weight for your boat and cargo? What you need to do is you need to figure out the volume of this thing that you see here, the hull, and multiply by 10,000 newtons per cubic meter. The volume would be in cubic meters. Notice that you've only got three parameters, you might call them, H, L, and A, that are not specified. The final answer is going to have to depend on those parameters. We're not going to get a specific number, though we could get a specific number if we plugged in specific numbers for A, H, and L. All right, so let's go ahead and solve this now. I would like to solve this in two ways using calculus, based on two drawings and two ways of cutting this three-dimensional solid, this hull. The first way is I'm going to cut it with slices that are perpendicular to a third axis along the length of the boat that you see here that I labeled with a Z going into the paper there. Cut it like this, perpendicular to that axis. When you do that, it is kind of nice because the cross-sectional areas that you get are all going to be the same no matter what Z is. It's a constant cross-sectional area in terms of Z. And what that means is if I can figure out what those cross-sectional areas are, once I figure them out, I actually don't have to do an integral anymore. I just need to multiply the cross-sectional area by L itself and I'll get the final answer. Of course, to find the cross-sectional area, I will have to do an integral, so you can't avoid integrals completely. The other way I'm going to do it is going to be with horizontal cross-sections. Down here, I will draw that when I get there. So it's a kind of an abstract problem. It's difficult to see what to do here, but remember, again, the final answer is going to have to depend on these unspecified parameters, the A, the H, and the L. So the question is how to figure it out in terms of those parameters. The cross-sectional area that you see there is the same as the area of this region right there at the front, where Z is 0, you might say. In order to figure out what that area is, I'm going to have to integrate. I'm going to have to integrate, if you think about it, the function whose graph is this horizontal line, the constant function y equals h, minus the parabola y equals ax squared. I'm going to have to subtract those functions and integrate that difference to find that area. But that does beg a question. What is the interval of integration? Evidently, it would be from, if you draw down perpendiculars here, this point right there to this point right here. And by symmetry, if we can find the x-intercept right there, I could integrate just from 0 to that point and then double the answer to get this cross-sectional area. Let's call this point B, just to give it a name. How do I figure out what B is? It does depend on A and H, evidently. Use the equation of the parabola. I'm going to know that when x equals B, y will equal h. I can replace y with h and x with b and solve that equation for b to see that it ultimately depends on h and a. Divide both sides by a, then take the positive square root of both sides. B is the square root of h over a, which I'm going to write as the square root of h divided by the square root of a. Okay? So now again, for the cross-sectional area, which is a constant in terms of z. So again, once I find this cross-sectional area, I just multiply by L to find the volume, and then multiply by 10,000 newtons per cubic meter to find the weight. I need to double the integral from 0 to b, which is square root of h divided by square root of a, of the difference, the constant function y equals h, minus the function y equals ax squared, which I write as just ax squared here. That's the integral to do to find this cross-sectional area. H is constant. Integrate h with respect to x, and get h times x. A is constant. I'm going to get a over 3 times x cubed. X goes from 0 to the square root of h divided by the square root of a. Plug in the numbers now. When you plug in 0, you get 0, so I can just plug in the top. I'll multiply the 2 back through. I'll get 2h square root of h over square root of a minus 2a over 3. I've got to cube this fraction. Square root of h cubed is h to the 3 halves power, or h times square root of h. Same kind of thing with square root of a cubed, a times square root of a. I do get cancellation of these a's here. I then need to get a common denominator of 3 times square root of a, so I got to multiply the top and the bottom of this fraction by 3. I'll get a 6h square root of h minus 2h square root of h all over 3 square root of a. 6 minus 2 is 4. That's going to give me 4. That's a 4 there. 4h square root of h divided by 3 square root of a. Okay. What is then the volume of the hull? Multiply that by L. Again, these cross-sectional areas are constant. I can figure out the volume then by just multiplying by L. Effectively, I'm integrating this constant function of z from 0 to L, but it's being a constant, it ends up multiplying just by L in the end. So I'll get 4h square root of h times L over 3 square root of a. And finally, the final answer for the maximum weight, I just need to multiply that by 10,000 10,000 newtons per cubic meter. This would be in cubic meters. Effectively multiply the 4 by 10,000 to get 40,000 h square root of h times L divided by 3 square root of a. So certainly if you knew the particular values of h, L, and a for your particular hull that looks like this, you can plug them in and figure out this weight in newtons. It's also interesting to think about this as a function, a multivariable calculus function of h, L, and a, and think about how changing h, L, and a affect the value of this function. For example, certainly if h and L increase this function, the weight that it can hold increases, and if a increases, the weight decreases. The effect of a is that it makes the hull skinnier and skinnier, and that is what this is telling you, is that this is going to mean that it can hold less weight when you make the hull skinnier and skinnier when a increases. All right, let's do this a second way now. Same kind of picture down here, but now I'm going to slice it with slices perpendicular to the y-axis. Those cross sections will look like this, and they will be rectangles. But they're not constant area rectangles. The area varies. When y is small, the rectangle's down here, and they're skinnier and they have less area. And when y is large, close to h, the rectangle has more area. So we are going to have to integrate to find the answer for the volume. Here we integrated to find the area, and then we multiplied to find the volume. Here we are going to do an integral right away for the volume, because the cross-sectional area is a function of y that is not a constant function of y. This distance right there is constant. That's just L. It's this distance right here that is not constant. What is it? For a given value of y, it would be double the distance from here to here. What is the distance from there to there? It would be the x-coordinate at this point minus the x-coordinate at this point, which is 0. In other words, what I need to do is I need to solve this equation for x, which is quite analogous to solving this equation for b, but I was thinking of h as a constant back up here. Here I'm thinking of y really as a variable. Divide both sides by a, I'll get x squared as y over a. So x is square root of y over a, which again, like before, is the square root of y divided by the square root of a. And I'm going to integrate with respect to y, so I think I'll write this as 1 over square root of a times y to the 1/2 power, because that'll make it a little easier to think about integrating it. That is x. That's this distance right here. It's not the entire distance. I need to multiply that by 2 to get the entire distance, and then multiply by L to get the cross-sectional area. So the cross-sectional area function as a function of y, that's going to be the function I integrate, is going to be 2 times this times L. I'll put the L in front. I'll have 2L over square root of a y to the 1/2. And that is going to mean the volume can be found by integrating that function from y goes from 0 up to h. 0 to h, 2L over square root of a y to the 1/2 dy. We should get the same volume that we got before. Then we'll have to, again, multiply by 10,000 newtons per cubic meter to find the final answer for the weight. Add 1 to the exponent, you'll get an exponent of 3/2. I got to divide by 3/2 as well, which means dividing by 3/2 is the same as multiplying by 2/3. Oh yeah, now you can see it coming together. 2 times 2 is 4, 4L, there's our 4. H to the 3/2 is the same as h times square root of h, all divided by 3 square root of a. I put the L over there instead of over there, but it is the same as this, right there. And that gives us the same final answer. I won't rewrite it for the weight. Multiply by 10,000. There we go. That is the maximum weight that the boat can hold.